Today's video features an area volume problem from the year 2015. This was a calculator active question, and I classify it as type 4 because it's area volume. They've provided us a graph here of two functions, f of x, which is this function here, and g of x, which is that function. And then they've marked region R and region S as the regions that are enclosed. In part A, we are going to find the sum of the area of region R plus the area of region S. So in order to do that, we first need to find the intersection of these two curves. So we're finding when does f of x equal g of x. Unfortunately, this is a calculator active question, and so we can turn to our calculator to find where these two curves are equal to one another. All right, so we're going to find the intersection of these two functions. We're going to do this graphically. So first thing you'll need to do is go to your y equals and clear out any equations that you have in there. And now my equations are clear, my plots are turned off, and I can start typing in the equations. I'm going to let f of x be 1 plus x plus e to the x squared minus 2x. Okay. And then my g of x, I'll put in y2, and that was x to the 4th, scroll right to get out of the exponent, minus 6.5 x squared plus 6x plus 2. Once those are in there, we can do a standard zoom. If we press zoom 6, that does a standard zoom on the graph. Going to take a little bit of time to draw. We start to see the graph. Now the graph that we have on our screen here is slightly different than the graph provided by the College Board, because the College Board zooms in on a specific location. If we wanted to make our graph look a little bit more like theirs, their x-min is probably around -1 with an x-max closer to 3, and then their y-min is -1 with a y-max closer to 5. And now if we graph that, we'll get something that's more closely resembling theirs. So the blue curve is f of x, and the red curve is g of x. So our goal here is to find the intersection. We're looking for where do these 2 points, or where do these two curves intersect. They provide us the first intersection and the last intersection, but we need to find this one. And it looks to be around x equals 1. So if we press second trace, that'll pull up our calculate menu. Option 5 is the intersect command. And first curve, we're on the blue one, so I can press enter. Second curve, we are on the red one, so I can press enter. And then finally, guess. My blinking cursor is already very close to the location of the guess, so I'm just going to press enter there. And we get an intersection at x equals 1.032. So that value might come of use later. Likewise, the y value might come of use later. So I'm going to store both of those as variables a and b. So if we quit to our home screen, we can go x store as alpha a. And that's now stored in the calculator, and alpha y will store as alpha b. Okay, so those are stored in the calculator should I need to use them later on. All right, let's go back to the drawing. Okay, so we have our point stored as a, and then our y coordinate we stored as the letter b. And we want to find area, so we're going to take a representative rectangle. I'm going to sketch this over here. And these little representative rectangles, the height of the rectangle, so the area of one would be height times our delta x. So that height is top function minus bottom function. So for region R, we're going to start at x equals 0 and finish at x equals a, and our top curve is g of x. Our bottom curve is f of x. and that's the area of region R. So we've got height, top minus bottom, times width of delta x. To that we add region S, which starts at x equals a and finishes at x equals 2. And for this portion, f of x is on top. So f of x minus g of x dx. And this will give us the area of the two regions. And they actually want us to evaluate that. Sorry, I should have had that shown. Okay, so let's grab our calculator and type this into the graphing calculator. And we do have these values stored in a and b. So by pressing math 9, we pull up our integral, and I can go 0 to a. And then f of x was y1, and g of x was y2. So by pulling up y2 minus y1, I save the problem of typing out the equation correctly, because it's going to call on the previously entered equations. To that, I want to add my second integral, math 9 from a till 2 of y1 minus y2. So vars y vars function, vars y vars function y2 dx. And this comes to a total area of approximately 2.004 square units. This is worth 4 points. The first point comes from having the correct limits, the second point comes from having the integrands, and the third is also integrands, and then finally the fourth point is from the answer. So 1 point for the limits, and then 1 point for probably doing each of the integrands, and then finally the last and fourth point comes from getting that value there. Okay, moving on to part B. Part B is a volume question, so I've projected the graph down into the plane so that I can do a three-dimensional extrusion. And it says region S is the base of a solid whose cross-section perpendicular to the x-axis. So perpendicular to the x-axis. The cross-section is a square, so this gets extruded upwards to make a square shape. And you can imagine that, you know, if you're over here, you're going to have a smaller square, and this expands out starting as a very narrow square up to a large square and then back down to a small square. So then the area of one of these squares, we could say, is the top curve minus the bottom curve, and that top curve was f of x minus g of x, and then the height of that is the same length, so that value squared is the area of one of them. If we do the volume of one of the squares, like if we extrude it out so that it's now a very thin slice of a rectangle, a rectangular prism, then our volume becomes that value f of x minus g of x squared times the delta x of the rectangular prism. So then the volume of the entire extrusion would be summing up all of these values that are infinitely thin. So starting at a and finishing at 2 of f of x minus g of x, quantity squared dx, because we've gone from the delta x to the infinitely thin slice of dx. This is our volume, and they want us to actually find the volume, so we need to then turn to our calculator and evaluate this. So math 9 pulls up our integrals. We're going from a to 2, and f of x was my y1, so vars y1, and g of x is my y2. For some of the more updated calculators, if you press alpha F4, you can also get your y values. So y2, that quantity gets squared dx. And we get a volume of approximately 1.283. Okay. Part B is worth 3 points. You get 2 points for the integrand. So 2 there, and then 1 point for the answer. All right. Let's take a look at part C. Part C, H is the vertical distances between the graphs of f and g in the region S. So h of x is the distance between f and g. So f is our top function, and g is our bottom function. Okay. Find the rate at which h changes with respect to x when x equals 1.8. So they're asking us to find h prime of 1.8. In other words, evaluate f prime of 1.8 minus g prime of 1.8. Very straightforward calculation, especially when we have access to our calculators. So our calculators can do the heavy work for us, evaluate the derivative at 1.8. So math 8, we're taking the derivative of y1 at 1.8. And from that, we're subtracting again the derivative, math 8, of y2, so alpha trace pulls up y's, at 1.8. And we get approximately negative 3.811, or if you round, negative 3.812. That's part C, and part C is worth 2 points. 1 point is if you consider h prime, and the second point comes from having the correct answer. All right, looking back at the key, it's probably safe to write in here h prime of x equals f prime of x minus g prime of x, just to fully support that we know what h prime is, though I think this would get us credit. All right, thanks for watching. Be sure to comment, like, and subscribe. Have a good day.